Welcome to step 3 of the TTP-based hunting methodology, determining data requirements. As a reminder, we'll review the overall methodology and curriculum, as well as what we'll cover in this module and how that fits into the bigger picture. The focus of this module is on determining the data required to test the hypotheses generated in the previous step. We'll go over some of the key aspects of data collection to keep in mind while deciding what to collect and the associated trade-offs. Finally, we'll return to our example technique and refine our abstract analytics into more structured queries. Recall that we're on the third step of the 7-step methodology. Remember that although this V diagram looks very sequential and clean, the actual process will involve lots of iterations and refinements. That's expected and usually beneficial. The methodology is structured in this way to provide a framework upon which you can build and iterate as you implement it. In step 3, we have an understanding of behaviors we're seeking and hypotheses and abstract analytics associated with them. In this step, we'll determine what data we need to test those hypotheses. At the end of this course, you should have the information you need to start implementing this process on your own. In addition to leveraging the work of the broader community, you'll be able to craft your own analytics and customize what you get from outside sources. At the conclusion of this module, you should have the knowledge you need to determine data requirements for an analytic and how to refine an abstract analytic into something more concrete. We'll go over some common data types and sources and see how those map onto analytics. Just like the previous modules, you should be familiar with Windows, an analytic platform like Splunk or Elk, the fundamentals of networking, and Attack before beginning this course. To gain hands-on experience, you should also have an environment which you can instrument to collect data and an analytic platform to experiment with your own analytics. In step 1, we studied adversary behaviors and TTPs, and in step 2, we created hypotheses and abstract analytics based on that information. In this step, we're going to develop data collection requirements associated with those hypotheses. By developing these data collection requirements, we'll be able to communicate effectively about what data we need to collect and, importantly, why we need to collect it, because each collection requirement can be traced back to adversary behavior we're trying to detect. Since we followed this process, we will have very specific recommendations about data collection and the configuration and placement of sensors to get that data. This provides a solid foundation for analyzing a system's existing instrumentation, making strategic modifications to that configuration to improve our ability to detect malicious activity, and insight into which adversary techniques might not be visible given a particular data collection posture. When we're developing data collection requirements, we'll need to balance precision and recall as we discussed in previous modules. Remember that precision is a measure of how few false positives our approach generates. Perfect precision means no false positives. Recall, on the other hand, is a measure of how many true positives we detect, relative to how many truly malicious events there are to detect. Perfect recall means no false negatives, because we're detecting all of the malicious activity. As we discussed in previous modules, these two aspects of detection are often in tension with each other. Improving precision often comes at the expense of recall because we're narrowing the scope of what is detected. Doing that can help reduce false positives, but might also cause some false negatives or missed detections. On the other hand, improving recall often causes reduced precision because the detection scope is made larger to reduce the false negatives. Although we typically think about precision and recall in the context of analysis and specific analytics, it's also a factor in data collection. Essentially, configuring a sensor is like creating a first-stage analytic. The configuration ends up filtering out some data while sending the rest to the analytic platform. So it suffers from the same tension between precision and recall as analytics do. If the data collection is too broad, it could cause an overload at the system level, like the bandwidth required to send the data back for analysis, or at the cognitive level for the analyst. For example, simply collecting all SysMon events without any filtering is likely to generate much more data than it's worth for detection. However, filtering out a lot of data through a narrow configuration might reduce false positives, but also blind the analytics to important information. Every exclusion in the data collection configuration is potentially a place for an adversary to hide. Similarly, overly specific collection scope can create a brittle instrumentation, which allows an adversary to more easily evade detection. For example, configuring a sensor to only collect process access events when the source image is exactly one specific path to an executable would be brittle to an adversary changing the name or location of the executable they use. It helps to keep the data collection strategy focused on behavioral invariance. Doing so helps optimize collecting robust events associated with the behavior without some of the lower value events. In addition to good insight into the malicious behavior you're hunting, it will help to be familiar with the common data sources available for the platforms you're hunting on. We'll review a few of these later in this module for Windows. As usual, it will also help to keep the 3 dimensions in mind while determining your data collection requirements: time, terrain, and behavior. We need to be sure our data collection plan will ensure the right information is collected while it is available, keeping in mind that an adversary might attempt to erase their own activity from logs. We will also need to think through all the terrain that needs monitoring across different levels of granularity. Are we monitoring the entire enterprise? Are we seeing network traffic between hosts, even if it doesn't cross the enterprise boundary? Will we get insight into inter-process communication on the endpoints? Are we covering all of the different technology types and device types in our network? And finally, we need to ensure we're collecting the data associated with the behaviors we're seeking to detect, along with whatever contextual data we'll need to differentiate malicious from benign, and to trace causal chains of events. Let's investigate each of these 3 dimensions and how they impact data collection. First, let's consider the time-based elements of data collection. We need to ensure data is collected when the adversary acts. This will help us detect the activity as soon as possible and increase our chances of taking effective action before the adversary has a chance to accomplish their end goals. Collecting during the event also mitigates the risk that the adversary will go back and erase their activity from logs. In addition to collecting when the malicious activity happens, we'll also want to collect during benign operations as well, to tune our analytics and reduce false positives and establish trends. Since we don't know in advance when the adversary will act, this usually means we'll need to continuously collect data. Continuous collection comes with some implementation costs and is sometimes impractical if, for example, some of the components of the enterprise are disconnected from central log collection for periods of time. Within the constraints of your environment, though, continuous collection will be preferable. In addition to collecting at the right time, we need to ensure we're collecting data from the right places in our network. Consider where in the network the behavior will be visible and plan to collect data there. Certain techniques are more visible within an enclave than at the network perimeter. Certain techniques will only be visible on the endpoint. You should also think through which types of devices and operating systems are relevant for the behavior in question. For example, detecting task scheduling will be optimized by collecting host-based event logs from all enterprise machines, both servers and endpoints, since that's where the behavior can occur. Detecting remote execution through remote task scheduling might also be visible by collecting network traffic from within the enclave. Finally, think through the behavioral invariance and contextual data required to detect the activity, distinguish malicious from benign, and connect the detection to the larger adversary campaign. In addition to the event types, which fields will be required or useful? Focusing on the behavioral invariance will help balance precision and recall during collection and create a more robust instrumentation plan. Let's review some common data sources for Windows as an example. Although this methodology is driven by an understanding of adversary behaviors, it is very useful to have a solid foundational understanding of the common data sources associated with the technologies you're hunting on. This makes it much faster and easier to determine a collection strategy. Just keep in mind that you'll be biased toward using familiar data sources, even if those aren't optimal. To facilitate the examples we use in this course, and since Windows is a commonly used technology, we'll review a few data sources available in Windows and on IP networks. If you're hunting in terrain that includes Mac or ICS or mobile devices, you'll want to get familiar with the typical data sources available from those technologies. Given the concepts you developed while thinking through the time, terrain, and behavior aspects of your collection needs, you can start mapping those onto the data sources available. What's available changes over time and is different for different technologies. We'll just cover a few representative examples like Sysmon and Windows Event Logging. Keep in mind that you might have a few different data sources that seem to provide essentially the same kind of data, but often there are differences in these that matter, such as which metadata fields they provide, or whether they provide continuous collection or are designed for snapshots. You'll have to apply the concepts from this module to your situation and adapt them as needed. For a typical enterprise network, there are some common data types available for collection. From devices such as desktops, firewalls, and routers, we could collect data about processes and files, or system and application logs. For an IP network, there are some typical data types like full packet capture and network flow. For each of these data types, there might be one or more collection sources for that type of information. For example, Windows Security Event Logging and Sysmon both provide information about processes and file activity on Windows. For Linux, you can configure auditd to collect similarly detailed host-based information. And there are some open source repositories of auditd configurations mapped to attack techniques you could use as a starting point. You can use a library like libpcap or npcap for packet capture on Linux or Mac or Windows. And you can use a tool like Zeek to ingest that PCAP, run analyzers on it, and produce a log of events. One data source MITRE has found helpful for detecting malicious behaviors on Windows is Sysmon. Sysmon is short for System Monitor and is freely available as part of Microsoft's sysinternals tool suite. It consists of a system service and associated device driver, and will monitor and log operating system activity to the Windows event log. Microsoft has continued to update Sysmon and add new events and capabilities. When this briefing was created, there were 24 total event codes, including activity associated with processes, network communication, DLLs, files, and the registry. Each Sysmon event contains two sections: a system section with fields associated with every type of event, as well as an event data section with additional fields specific to that event type. You can check the current Sysmon configuration on your machine by running sysmon-s. Within the event data section of Sysmon events, there are a few fields that are commonly present. The rule name field is defined in the config file and can be used to label the event to provide some context about why the configuration was set for this event to fire. One example use for this field would be to include the attack technique or techniques that drove the inclusion of this event in the data collection strategy. Each event will also record the UTC time the event was triggered, as well as the ID of the process that created the event. Bear in mind that the process ID is the ID used by the operating system and can be recycled once a process terminates. So, the process ID field is not guaranteed to be unique. However, Sysmon also provides a process GUID, or Globally Unique ID, derived from the process ID, the machine's GUID, the process start time, and the token ID associated with the process. It is extremely unlikely for this process GUID to be repeated accidentally, and is a more robust way to track processes across time and machines. Sysmon also provides information about the path to the file in question in the image field. And in the case of an executable, it also provides the original file name. The image field provides some additional context about where the file is stored on disk, but will change if the file or executable is moved. On the other hand, original file name is derived from the portable executable header and would stay consistent even if moved to a new location. Similar to process GUID and process ID, these two fields seem similar but have different attributes, and each is more appropriate for different use cases. Finally, Sysmon can be configured to compute and log various hash values of the image associated with an event. Monitoring these hash values can be combined with the use of original file name, for example, to make it much more difficult for an adversary to modify legitimate images or rename their own to blend in. One of the most useful events produced by Sysmon is event code 1, process creation. This event is triggered whenever a process is created, as the name implies, and provides valuable information about that new process. These additional fields can be used in the filtering step during data collection, as well as in analytics. In addition to the fields we've already reviewed, process creation events include the full command line associated with the process creation, which can provide great insight into the command line activity and help distinguish malicious from benign use. There's also valuable information about the parent process, which created this one, including the globally unique ID and its command line arguments. Sysmon also provides useful information about the session and integrity level associated with the process. Each of these fields can help distinguish malicious activity from benign and provide context during an investigation. Another event that can provide detailed insight into malicious behavior is event code 7, image loaded. Several attack techniques touch upon the loading of or manipulation of loading DLLs, and this Sysmon event gives us visibility into that activity, along with associated information like which DLL was loaded and its signature, which can help distinguish malicious from benign activity. Sysmon can also generate alerts on file activity, such as creation. As in the other event types, the additional field information can be very helpful here in configuring Sysmon itself to balance precision and recall, as well as in analysis. As one last example, Sysmon can also create events around registry activity. Similarly with the other event codes, the registry events contain useful fields for collection, configuration, and analysis, such as the name of the registry key and sometimes the value it was set to. When you view an actual Sysmon or Windows event in your analytic platform, you'll see these fields and values broken out something like these screenshots. In addition to Sysmon, Windows has extensive native logging capability with a lot of different and valuable event types, which tend to provide complementary value to what Sysmon provides. There are far too many event types to review in this course, and we recommend you read documentation on Sysmon, Windows Event Logging, and any other logging capabilities available in your environment. A sample of interesting native Windows log events includes logon events, registry activity, process creation, an event specific to scheduled task creation, which we'll use in our examples, network activity, and service creation. Just like with Sysmon, each of these events is populated with additional fields and values, providing more context about the event to help with analysis. Let's return to our example technique of scheduled task. As we've discussed in previous modules, adversaries may use task scheduling to execute programs for persistence, or to run a process as a specified user, or to execute a process on a remote machine. Our hypothesis development and research from step 2 led to a component hypothesis about the persistence use case focused on the behavioral invariance of job file creation and task registry key creation. We created an abstract analytic based on that hypothesis around the events of file creation or registry modification. Based on our open source research in step 2, we uncovered several ways to schedule a task. By knowing our available data sources, we also know that event code 4698 from Windows Event Logging seems pretty great for detecting this technique. In step 2, we did some hands-on experimentation as well, and scheduled tasks while observing what happened through Procmon and WinDebug. Now in step 3, we look more closely at the data sources to check which events are triggered by this activity and what their field values are for different implementations and use cases. Let's briefly review what we discovered in step 2 during our research into this technique and note how these activities look in the logs. As you recall from step 2, we scheduled tasks in various ways and observed the underlying behavior using Procmon and WinDebug. Procmon gave us insight into the registry and file activity associated with task scheduling. We got insight into the registry keys created and the location of the job file creation. We also gained insight into the DLLs used and when event 4663 and 4698 were triggered. Now, in step 3, we look more closely at the logs generated by this activity. Event code 4698 will be triggered whenever a task is scheduled, including in benign situations. If we break up the technique as we did during hypothesis decomposition, we can analyze the differences in 4698 field values for the various use cases. For example, if we're seeking task scheduling which specifies a different user to run the task as, we can look for 4698 fields which change when that occurs relative to scheduling a task to run as the current user. After implementing the behavior a few times, with and without specifying a different user to run as, we notice that the registration info author field seems to document the user scheduling the task, while the principal XML element seems to contain the user to run the task as. Based on this insight, we can refine our abstract analytic to focus on detecting when those two specific XML element values are different. So far, our investigation has been based on our own experimentation and implementation of the behavior. Before we go too far with that, let's check what these event log fields look like for tasks being scheduled by others, like Microsoft applications. It turns out that the registration info author element is not always set at all and is sometimes set to the name of the vendor rather than a username. If we write an analytic based on registration info author being different from the principal user ID, it will alert on these typical and benign activities and create false alarms. Further investigation uncovers two other fields in the 4698 event called subject username and subject domain name, which seem to consistently represent the domain and user scheduling the task for our experimental implementations as well as the tasks scheduled by applications. Based on this further research into typical benign activity, we can update our abstract analytic again to focus on subject domain name and subject username being different from the author value within the principal XML element. In step 2, we also found some candidate behavioral invariants associated with task scheduling on Windows, such as job file creation, task registry key creation, network traffic to the task scheduler service for remote scheduling, and certain DLL loads. We summarized those behavioral invariants in this table. Now, in step 3, we can add data sources to this view. Each of the behavioral invariants is associated with one or more log events or network activity sequences. We can start by listing those potential data sources and then documenting which fields and values we'd want to access for analytic filtering. For example, if we monitor process creation events, we'll want a field like image or original file name to help narrow the results to just those executables associated with task scheduling, like at or should tasks. Similarly, we have insight into specific DLL names, port numbers, registry key names, and directory names associated with these behavioral invariants, and we'll want to be sure we collect the required fields for each of those events. Finally, as we investigate the potential data sources and review events that fire during the sequence, we discover that the 4698 event is triggered after the final registry modifications, which occur after the job file is written. Each of these data collection possibilities comes with pros and cons, often associated with precision and recall. So documenting those will help prioritize our data collection requirements. For example, if we plan to collect process creation events and filter them based on image, how will we detect task scheduling done through the API using a custom executable? If we collect image load events and filter to those loading MSW sock.dll, how will we filter out what is likely to be many other such events unrelated to remote task scheduling. What if administrators or the adversary modify the default values for the port numbers or job file location in our network? For event 4698, could an adversary directly write the appropriate job file and set the registry keys directly in such a way that a task is scheduled without triggering that event? Given this new information about data sources, we can refine our abstract analytics. Let's take a look at how to convert our abstract analytics into something more concrete and connect them to a data model and write them in a more formal syntax. Finally, we'll review some examples and present an exercise for you to practice. Recall from step 2 our descriptions of a hypothesis and an abstract analytic. A hypothesis is a proposed explanation made on the basis of limited evidence as a starting point for investigation. It's written in an informal language and at a high level of abstraction. An abstract analytic tends to be more detailed in its description of when it should be triggered. Now we'll take a look at more concrete analytics. These are executable queries written in a formal syntax and with specific data sources. For our example scheduled task technique, we wrote a hypothesis that if a new job file or task registry key is created, an adversary may be attempting to gain persistence. We also converted that hypothesis into an abstract analytic that got more specific about when it should be triggered, including the specific directory in which the file would be created and the specific registry keys we want to monitor. Now that we know about the 4698 event and how it is structured, we can write a more concrete analytic that will fire when a 4698 event is logged. Alternatively, we could use the more fundamental events 11 and 12 for file and registry key creation and use our abstract analytic information to filter those down to just the relevant events. In these examples, the concrete analytic syntax is Splunk. This could also be Elastic or the syntax of your choice. To detect remote execution through task scheduling, we developed the hypothesis that should tasks being executed with the /s argument or @ with the / computer name argument would indicate remote execution. We created an abstract analytic associated with that hypothesis, which specified the use of process creation events and filtering based on command line arguments. At this stage, we know about Sysmon event ID 1 and can specify a concrete analytic, again in Splunk syntax for this example, using that specific data source. Finally, we also developed a hypothesis and abstract analytic associated with the use of task scheduling to get a task to run as a specified user to get the privileges associated with that user. With our additional insight into the 4698 Windows event structure, we can convert our abstract analytic into something concrete. Again, we've used Splunk's syntax for our example, and now know enough to specify the exact data source, event ID, and field names to use, along with the Splunk syntax to parse and compare those fields according to the logic of our hypothesis. In each of our example concrete analytics, we used Splunk's syntax. How can we create concrete analytics that aren't tied to one specific analytic platform. If we want to share analytics with others, it would be nice to have a more generic language that provides the concrete specificity we want, while also providing flexibility to easily implement it in different platforms. One solution for this situation is to use Sigma. Sigma is a platform-agnostic, generic language to describe concrete analytics. If you write a query in Sigma, you can also use existing converter tools to translate the query into Splunk, Elastic, or another platform syntax. Sigma is also a repository of such analytics on GitHub. Each analytic can be labeled to indicate which attack techniques or sub-techniques it is designed to detect, along with metadata about things like false positives. Let's review this syntax so you're familiar enough to peruse the Sigma repository and consider those analytics for use in your environment, and also be prepared to start writing your own Sigma analytics. Sigma calls these analytics rules. Sigma analytics, or rules, are written in YAML. Field names are followed by colons and then the value for that field. Each Sigma analytic has a title as well as analytic components, including the data source and the logic to control when the analytic should be triggered. Sigma rules can optionally also include other information, such as a description of the analytic, the author, attack techniques or sub-techniques associated with the rule, or expected false positives to watch out for. So here's an example Sigma analytic from the GitHub repository written by Florian Roth. The title and description indicate that this Sigma rule is designed to detect multiple failed logins with different accounts from a single source system. It uses Windows Security Log, event IDs 529 and 4625, which indicate logon failure events, and 4776, which is associated with logon attempts, as input data sources. The timeline field indicates it will look over the last 24 hours, and the condition field indicates it will trigger when more than 3 different usernames trigger one of those 3 events from the same source workstation over those 24 hours. To put this in terms of the dimensions of time, train, and behavior, this analytic is selecting a logon failure behavior and counting occurrences in a 24-hour time window for each workstation in the terrain dimension. Here's another example Sigma analytic designed to detect task scheduling, again written by Florian Roth. The description indicates this analytic is designed to detect rare scheduled tasks, assuming that benign scheduled tasks will be common across the enterprise terrain. In this example, the analytic is helpfully labeled with the attack tactic of persistence and the sub-technique of scheduled task. It will leverage the Windows Task Scheduler application log, event 106, and find task names that occur fewer than 5 times in a 7-day period. The analytic notes that some software installations might cause false alarms. As an exercise, try filling in the blanks of this Sigma analytic or rule. As indicated by the attack labels, this analytic should still be focusing on detecting scheduled tasks, but use the knowledge you've gained from these briefings and your own research to implement a different approach from what we saw in the previous slide. Can you use some of the language from our hypothesis to create a title or description? What would you add or change? which Windows log source would be appropriate? And which event ID would you use? How would you specify the time frame and condition to leverage behavioral invariance specific to the specified user use case? What would you want to document regarding possible false positives to help others reuse your analytic? Pause the video and give this some thought. Try to fill in these blanks. And when you're ready, you can hit play and resume. Okay, in steps 1 through 3, we've studied adversary behaviors, found behavioral invariance, developed hypotheses and analytics, and identified useful data sources. These steps can be performed by the broader community and might not be suitable for your particular environment. So the next step will focus on filtering down the analytics and data collection requirements based on the mission, technologies, and priorities of your network. In step 5, we'll discuss how to evaluate an environment's existing data collection, identify gaps, and develop strategies to deal with those gaps. With as many of those gaps closed as possible, we'll move to step 6, where we implement, test, and tune our analytics. By emulating threat activity in our production network and validating that our analytics have good precision and recall, we'll be in a great position to conduct a thorough TTP-based hunt in step 7. To wrap up this step, and before you do the exercises that follow, let's take another look at the V. Through these first 3 steps, we've done a lot of research and developed analytics and data collection requirements. In the next step, we'll pivot into the implementation phase. As we move back up the right side of the V, we'll put these ideas into practice and put our analytics to the test so we're ready to hunt.